Hello everybody. I hope you are keeping super well and are in the highest of your spirits to learn something very nice today. Well, if I remind you what we did in the last lecture, we had witnessed the article of algebra of limits. Well, why was this article taught to you? This article basically taught you how to evaluate the limits of algebraic combinations of two functions, right? We witnessed the very first algebraic combination of two functions to be what? Well, suppose you have a function f, another function g. What if I combine these two functions by the algebraic operation of addition? In that case, you are going to obtain the function f plus g, isn't it? That's the first way in which I can combine two functions algebraically. The question is, if you wish to evaluate the limiting behavior of the sum function at the point C. Suppose you wish to evaluate the limiting behavior of the sum function at the point C, what did you do? What did I teach you in that? Well, just if you are aware about the limiting behavior of the individual functions involved in this combination at the point C, you will be able to evaluate the limiting behavior of the sum function at the point C, isn't it? Why? Because the limiting behavior of the sum function at the point C is nothing but it is given by the sum of the limits of the two individual functions at the same point C. Why? Because this is equal to limit of the function f as x approaches C plus limit of the function g as x approaches C. That means, just if I give you umpteen number of information about the limiting behavior of f at C, limiting behavior of g at C, you will be able to give me the limiting behavior of the sum function at C, isn't it? Next, suppose I have two functions f and g which I combine algebraically by the difference operation. That means I obtain a new function known as f minus g of x. Now the question is the same. If I wish to evaluate the limit of this difference function at the point C, what do I wish to do now? What have I have to do in order to evaluate the limit of the difference function at point C? Well, just if I know the limiting behavior of the individual two functions involved in the difference at the point C, I will be able to find out the limiting behavior of f minus g at C, because this is nothing. What happens over here? The limit gets distributed over the difference sign and you obtain limit of the function f at C minus the limit of the function g at C. Similarly, now see, there are many algebraic operations which can be used to combine two functions together to create new functions. If I have two functions, I can add them to create the sum function. If I have two functions, I can take the difference of them to create the difference function. If I have two functions, I can take the product of them to create the product function, and therefore the next query is regarding f into g of x. Well, just to evaluate the limiting behavior of f into g at C, what is enough for me? Sufficient for me is give me the limiting behavior of the two individual functions involved in this algebraic combination, and I will be able to give you the very limiting behavior of this product function. Why? Because if you give me the limiting behavior of f at C, if you give me the limiting behavior of the second individual function g at C, I will just take the product of them and I will obtain the limiting behavior of f into g at C. Yes, this is equal to nothing but limit of f at C multiplied by limit of g at C. Exactly in a similar fashion, we had also done how to evaluate the limit of f by g of x at C, provided this g function is not identically equal to 0, so that f by g is a well-defined quotient function, right? We observe that limit of f by g at c can be obtained by just taking the quotient of limit of f at c with the limit of g at c. Provided this limit is non-zero, this complete limit is a real number, and provided gx is not an identically zero function, f by g is a well-defined quotient function. Right? Again, the thing that I want to stress upon is that in order to evaluate, in order to determine the limiting behavior of the algebraic combination of two functions, it is right now it's evident to us that just we should be aware about the limiting behavior of the two individual functions involved in that algebraic combination. Just if we are aware about the two individual functions, limiting behavior about the two individual functions at the point C involved in the algebraic combination, we will be able to determine the limiting behavior of the algebraic combination of those two functions at the point C. That is what is evident by these examples. In fact, there was one more property which said that if you have the algebraic combination of two functions as this, that one function is the power of some other function. Something like this, fx to the power gx. Then how do you evaluate the limit of such algebraic combination of two functions at a point C? Again, the answer is same. To evaluate the limiting behavior of the algebraic combination of two functions at point C, you should just be aware about the limiting behavior of the individual functions involved in the algebraic combination at the point C. Because if you are aware about limit of f at C, limit of g at C, what is the limit of f to the power g at C? It is nothing but limit of f at C to the power limit of g at C. That means one thing which is being portrayed through these 5 properties distinctly is that just make me aware about the two individual functions involved in the algebraic combination, their limiting behavior you make me aware about. I will give you the limiting behavior of any combination, any algebraic combination of them, right? But is that true always? Is that true always that by merely knowing the behavior, the limiting behavior of the individual paths, we can evaluate the limiting behavior of the overall expression? Is that always true? Well, if I just give you a small example, suppose I say find out the limit as x goes to 3 by 4 of x cos x. Fine. Over here you can see x is one function playing the role of f and cos x is one complete another function playing the role of g, isn't it? Here I am saying find out the limit of the product of two functions. Well, by the properties that we have done, the answer is that if you wish to find out the limit at a point C of the product function, just keep yourself aware about the limit at point C of the individual functions and you will get the limit at point C of the product function. So what is the limit at the point 3 by 4 of the function f, which is x? Limit x approaches 3 by 4 of the function x, you know it is 3 by 4. And what is the limit at 3 by 4 of the function g, the next individual function involved in this combination? It is cos x. So what is limit x goes to 3 by 4 cos x? It is nothing but cos 3 by 4, right? This is a real number, this is a real number, and therefore by the property that we have done, we know that limit at 3 by 4 of fx into gx is nothing but limit as x goes to 3 by 4 of fx multiplied by limit as x goes to 3 by 4 of gx, right? Which gives you nothing but 3 by 4 cos 3 by 4, which is definitely a real number. That is what we have done, isn't it? If I had something like the quotient, what would I have done? Suppose I ask you to evaluate limit x goes to 1 e to the power x upon sin x. It's evident to you that this is the algebraic combination of two functions e to the power x and sin x, where the algebraic operation involved is division or quotient. Here, quotient of these two functions has been taken to create a new function which is e to the power x upon sin x. I am asking you to evaluate the limiting behavior of such an algebraic combination of these two functions. In order to evaluate the limiting behavior of the algebraic combination of two functions, by the properties that we have done till now under the algebra of limits, the hint is that you should be aware about the limiting behavior of the individual functions involved in the algebraic combination. So the individual functions, one is e to the power x, one is sin x. So you should be aware about the limiting behavior of these two individual functions. So what is the limit of e to the power x as x goes to 1? You know it is nothing but equal to e to the power 1. And what is the limit as x approaches 1 of the other individual function sin x? It is nothing but sin 1, right? That is what it is. So that means over here, this is what you are getting. So once you are aware about the limiting behavior of both these individual functions at the point 1, by the property I know that the limiting behavior of f by g at 1 is nothing but limit of f at 1 upon limit of g at 1. So what is this? Therefore, limit of e to the power x upon sin x as x approaches 1 is nothing but limit of e to the power x as x approaches 1, which is e to the power 1, upon limit of sin x as x approaches 1, which is sin 1. Obviously, this is a finite real number. Understood? That means now things are looking pretty easy and pretty nice to us. Why? Because give me any algebraic combination of two functions, I just need to be aware about the limiting behavior of the individual functions at point C, and I will be able to evaluate the limiting behavior of the algebraic combinations of those two functions at point C. Well, world is not that beautiful always, situations are not that ideal always. Why? Because no, it's not always true that just by merely knowing the individual limiting behavior of the two functions involved in the algebraic combination gives you sufficient information about the limiting behavior of the algebraic combination's behavior. It is not at all necessary, it is not at all a compulsion. Over here, the ideal situation was arising in this example and in this example, wherein the limiting behavior of the product was coming out to be evaluated very nicely just by knowing the limiting behavior of the individual functions at the same point. Here also, very ideal situation, limiting behavior of the quotient was coming out to be evaluated very nicely just by the information, just by the simple information of the limiting behavior of the two individual functions involved in this quotient. But as I told you, it's not always the case. And what is the evidence that I have for this? The evidence that I have for this is going to be presented to you in the name of the next topic, which is one of the most important, most interesting and exciting topics, which is indeterminate forms. Indeterminate forms. Well, before I begin, as I have already told you what this article is going to deal with, this article is going to stand as the evidence for my statement. My statement was, no, it's not always true that just by knowing the limiting behavior of the two individual functions involved in the algebraic expression, you will be able to evaluate the limiting behavior of the overall algebraic expression. Right? That's what my statement is, and I am telling you right now that this article is going to stand as the evidence of that statement. Okay? Before I portray to you how this is basically standing as the evidence to just develop your conviction over my statement, let me begin with the simple placid meaning of indeterminate. Indeterminate means something which cannot be precisely determined. not precisely or uniquely determined. Or I can say something which is not definite, something which is not definite, something which is indefinite can be termed as indeterminate. So, indefinite. Something which is not definite, okay? It can change, it can vary, okay? It can alter, and therefore, indeterminate creates ambiguity. It creates a cloud of confusion, a cloud of doubt, because this is not a definite value. It is indefinite, it can change, it can vary, it can alter, and therefore ambiguity is something which is concerned with this word. Wherever there is indeterminate form arising, indeterminate situation arising, indeterminate condition arising, there is ambiguity involved. A lot of confusion, a lot of doubt gets created in that situation. So therefore, ambiguous, which means confusion, is also one of the synonyms of indeterminate. Okay? Now, when can I say a form of limit is an indeterminate form? Let me write that down, and then slowly and steadily you are going to relish the very evidential behavior of this topic. Okay? Certain forms of limit. So basically we are doing the chapter limits. So over here I am writing certain forms of limit are called indeterminate forms. That means over here till now one thing is evident, that there will be certain types of limit, certain limits of a certain structure which will be known as limit of indeterminate form. Okay? What are those limits? How do they look like? How are we going to identify them? All those things we have to learn. But till now one thing is evident, that there will be a certain type of looking limit which I am going to declare that it is an indeterminate form of limit. So certain forms of limit are said to be indeterminate forms when merely knowing the limiting behavior of individual parts of the algebraic expression So what have I written? When merely knowing the limiting behavior of the individual parts of an algebraic expression is not sufficient to determine the overall limit. See, the definition itself is standing as the evidence of my statement. I told you it is not always a compulsion that in order to evaluate the limiting behavior of the algebraic combination of two functions, just the limiting behavior of the individual two functions involved in that algebraic expression is sufficient. No, it's not always just sufficient. That's what it's written over here. Certain forms of limit are said to be indeterminate forms of limit when just knowing the limiting behavior of individual parts of that algebraic expression is not sufficient to determine the overall limit of that algebraic expression. Okay? Such are the forms of limit known as indeterminate forms. Now, how to look at them, how to believe that they exist? How do they look like? How can we identify them? What do they resemble? All those things slowly and steadily we are going to learn, and then we are going to be able to identify very easily the indeterminate forms. So let's begin with the very first type of indeterminate form. The first one is, let's see, it is called indeterminate form of the type 0 upon 0. Indeterminate form 0 by 0. Now what is this? When do you say a limit is of the indeterminate form 0 by 0? Okay? This particular article is going to say that whenever the algebraic expression whose limit needs to be evaluated at a point C is expressed as ratio of two functions f and g such that both f and g approach to 0 as x approaches C. Such forms of limit are called indeterminate form zero by 0. So now see, the moment you see 0 upon 0, you have to understand that such is the limit which arrives to be the answer of the algebraic expression which is of the form f upon g. See what is written. Whenever the algebraic expression whose limit needs to be evaluated at a point C is expressed as ratio of f and g. Whenever you have an algebraic expression of the form f upon g, whose limiting behavior needs to be evaluated at a point C, this is of the first type, right? Here what is going to happen? Till now under the algebra of limits topic, we have learned that if you have an algebraic expression of the form f upon g, whose limit needs to be evaluated at point C, in order to evaluate that limit, what you have to do? You have to know the limiting behavior of f at C, you have to know the limiting behavior of g at C and just divide them. Limiting behavior of f at C divided by limiting behavior of g at C, and what you obtain is the real number, which is limiting behavior of f by g at C. It is this particular thing which this particular type is violating. It is saying that indeterminate form of the type 0 by 0 occurs when you have the algebraic expression of the form f by g, whose limiting behavior needs to be evaluated at point C, and when you are segregating this limit to the individual expressions f and g, that means when you are finding out the individual limits of f and g at C, they are coming out to be 0. Limit of f at C is 0 and limit of g at C is 0. Then what you obtain is a 0 by 0 form. That means what is this trying to say? It is saying limit x tends to C of f by g of x. Suppose this is what needs to be evaluated. Fine. Till now we know that to evaluate this we just need to segregate the limits at f and g of f and g at C, and then you get the limit of f by g at C. But what if when you do that, what if when you do that, what you obtain is this. Is this a real number? Not at all. This is an undefined term. It's not a real number. How can you say that by just knowing the individual limiting behavior of f and g at C, I am able to know the limiting behavior of f by g at C? Well, if that would have been the case, 0 by 0 would have come out to be a limit, a real number. But that is not happening. That means it's not always true that by just knowing the limiting behavior of the individual functions involved in the algebraic expression, you can evaluate the limiting behavior of the overall algebraic expression. Right? Let me show you certain examples. Certain examples to illustrate the indeterminate form 0 by 0. Let's do that. The first example says what? Now till here you would be knowing, okay, I have understood that it's not happening always what algebra of limits was trying to say, but then why indeterminate? Why is 0 by 0 form of limit is said to be indeterminate? Where is ambiguity involved? Why is there indefinitiveness over here in the case of indeterminate form of 0 by 0? Why is it being called indeterminate? Let's find out through these examples. Suppose I ask you to evaluate limit as x approaches to 0 of this expression, f by g, fx equals x, gx equals x square. Fine. This expression only, it's being copied over here with fx replaced by x and gx replaced by x square. What you have to do? Over here, if you apply the concept of algebra of limits, what you are going to do is limit x tends to 0 f of x upon limit x tends to 0 g of x. Limit x tends to 0 f of x is 0 and limit x tends to 0 of x squared is also 0. Right? So you know the limiting behavior of both the functions individually. It is a real number 0, it is also a real number 0, right? But limiting behavior of f by g is not coming out to be a number of the form limit of f upon limit of g. That means this is not a real number. Now over here a question arises. A question which arises is that if this is the form which is occurring by distributing the limits of f and g at C at 0 over here, I am not getting a real number as the limit. Does that mean that limit of x upon x squared does not exist? Of course it exists. How? See. This thing, you know, if x is approaching to 0, x is a number very, very close to 0. It is not equal to 0, it is very, very close to 0. That means always x is either positive or x is either negative. It is never 0. And when x is not 0, I can cancel these x's with each other. I am going to left with this, which is infinity. Right? That means this function x upon x square has limit infinity, or basically I can say it is diverging to infinity, right? Whereas, let me show you one more example which is going to boggle you. How? Let's see. Suppose I say find out the limit as x approaches 0 of the expression, algebraic expression x upon x. Now over here again you have f upon g, where fx is x, gx is x. Is it sufficient to know about the limiting behavior of f at 0 and g at 0 separately to calculate the limiting behavior of f by g at 0? No. Why? Because if you know the limiting behavior of f at 0, and you know the limiting behavior of g at 0, and you do this by taking the inspiration from algebra of limits topic, you are going to get 0 by 0, which is not a real number. Does that mean that the limit of x upon x as x approaches to 0 does not exist? Of course it exists. Let's see. Well, over here we saw that the limit was coming out to be infinity. The limit of an algebraic expression of the form f by g, which is basically giving you 0 by 0 form, actually is, after algebraic elimination procedure, the limit is coming out to be infinity. Well, x by x is another expression of the type which is giving you 0 by 0 in its form. The limit form of f by g over here is 0 by 0. But